The topic for this video is Module 3, Inputs and Tools, Chapter 8, Quantitative Concepts for the CFA Institute Investment Foundations Program. So here we are in Module 3, Inputs and Tools. The topic for today's video is Chapter 8, Quantitative Concepts, which is a little bit of math and statistics, but don't worry, you're not required to do any calculations on the exam if you don't have any background in math whatsoever. Even at basically high school level, you'll find that it's not too difficult, okay? And if you've got some background in math, you'll find that this is a relatively easy chapter. There are 10 learning outcome statements for this chapter, and as you can see, there are 64 questions in practice questions in the learning ecosystem. In general, on average, not too bad. The learning outcome statements for this chapter are A, define the concept of interest. B, compare simple and compound interest. C, define present value, future value, and discount rate. D, describe how time and discount rate affect present and future values. E, explain the relevance of net present value in valuing financial investments. F, describe applications of time value of money. G, explain uses of mean, median, and mode, which are measures of frequency or central tendency. H, explain uses of range, percentile, standard deviation, and variance, which are measures of dispersion. I, describe and interpret the characteristics of a normal distribution. And finally, J, describe and interpret correlation. Learning outcome statement A is define the concept of interest. Borrowing and lending are transactions with cash flow consequences. Someone who needs money borrows it from someone who does not need it in the present, a saver, and is willing to lend it. In the present, the borrower has money and the lender has given up money. In the future, the borrower will give up money to pay back the lender, and the lender will receive money as repayment in the form of interest. The money originally borrowed, which interest is calculated on, is called the principal. Interest can be defined as a payment for the use of borrowed money. The borrower pays a price for not being able to wait and to compensate the saver for giving up potential current consumption or other investment opportunities. That price is interest. Interest is paid by a borrower and earned by the lender to compensate for opportunity cost and risk. Opportunity cost in general is the value of alternative opportunities that have been given up by the lender, including lending to others, investing elsewhere, or simply spending the money. Opportunity cost can also be seen as compensation for deferring consumption. The lender also bears risk, such as the risk of not getting the money back if the borrower defaults, which is a failure to make a promised payment. The riskier the borrower, or the less certain the borrower's apparent ability to repay the loan, the higher the level of interest demanded by the lender. So higher risk, higher rates. Another risk is that as a result of inflation, prices of goods and services increasing, the money received may not be worth as much as expected in the future. In other words, a lender's purchasing power may decline even if the money is repaid as promised. The greater the expected inflation, the higher the level of interest demanded by the lender. Learning outcome statement B is compare simple and compound interest, okay? So we have two tables here. The first table is interest earned on a £100 deposit in 2 years using simple interest. And the rate that we're using is 10%, okay? And in the second table, it's interest earned on a £100 deposit in 2 years using compound interest, again using the same 10% interest rate. So if we start with the simple interest, the underlying assumption of simple interest is that interest is not reinvested, and thus it is calculated on the amount of the original principal. So you can see here that £100 times 10%, the interest earned is going to equal £10, which is really easy. Just bring up the calculator. 100 times 0.1, 10%, equals £10, okay? So therefore, the ending balance at the end of the first year is £110. Now in the second year, the interest is still being calculated on that original principal amount. So it's 100 times 10% equals 10 pounds. So 110 pounds, the beginning balance of year 2, plus the 10 pounds interest in year 2, we're going to have an ending balance at the end of year 2 of $120, which is easy to understand. We started with 100 pounds. We earned 10 pounds interest in year 1. We earned 10 pounds interest in year 2. So we have an ending balance of 120 pounds. So you can see the interest being earned is the same every year because the interest is being calculated on the initial principal or the beginning balance. Now, however, when we move to compounding interest, you can see that in the first year it's 10%, so it's the same calculation. 100 pounds times 10%, we're going to earn 10 pounds of interest. So at the end of the first year, you can see our balance is exactly the same, regardless of whether we're using simple interest or compounding interest. However, when we're looking at compounding interest, we're earning interest on interest. So we're going to use the beginning balance at the beginning of year 2, and we're going to multiply that by 10%. So we can see now our interest in year 2 is $11, 110 pounds. Sorry, pounds. We're talking about pounds. 110 pounds at the beginning of year 2 times 10%. And we've got 11 pounds interest in year 2. So the ending balance at the end of 2 years is 121 pounds. Ending balance at the end of year 1 is beginning balance at the beginning of year 2. 110 pounds plus 11 pounds, 121 pounds. Okay? So compounding interest is extremely powerful. Reinvesting the interest earned on previous investments is a way of growing savings. As illustrated in this panel, in this table, the person who invests 100 pounds at 10% for 2 years will end up with 1 pound more with compound interest, 121 pounds versus the 120 pounds. This amount may not look very impressive, but when we look at a longer time period, say 20 years, you're going to see that the result is dramatically different. We're going to see that in the next couple slides, okay? So we're continuing with this concept of simple and compound interest, okay? So one of the things that we're going to look at this slide, and you don't have to memorize this formula, it's just that we want to understand the concept, okay? But here, the future value for simple interest, the way that we can calculate it is the original principal times 1 plus the simple interest rate times n, and the n is the number of years, okay? But when we're looking at compound interest, the formula that we can use is the original principal times 1 plus the simple interest rate to the power of n, and that's where we get the power of the compounding. So if I just bring up the calculator here very quickly, you can see that for 100 pounds, 10% per year for 2 years, the way that we would calculate it, we would start in the bracket, so it would be 0.1, the 10%, times the 2 years, plus 1, and then we would multiply it by the 100 pounds. So we're going to multiply that by 100 pounds, and we've got our 120 pounds at the end of 2 years. Okay, but when we're doing the compounding, the way that we're going to do it is 1 plus the simple interest rate, 10% to the power of n, which is 2 years, and then we're going to multiply it by the 100 pounds. So that's going to be 1 plus 0.1 y to the x to the power of 2, and then we're going to multiply that by the 100 pounds original principal, and you can see that at the end of the year, end of 2 years, we've got 121 pounds. Okay, so that's the example that we saw from the previous table. Again, another quick way of doing it, if you don't like the algebra to the power of n, you can just say we started with 100 pounds, we earned 10% for the first year, so we'll multiply that by 1.1, and then we earned 10% for the second year, so we're going to multiply that by 1.1 again, and you can see I've got the same result after 2 years on my 100 pounds becomes 121 pounds, okay? But as we said, the issue is the difference in the 1 pound is not much after just 2 years. But if we look at an example of 20 years, comparing 20 years, you'll see that the result is quite dramatic, when we're earning interest on interest or earning compound interest, okay? So let's just bring up the calculator again and do that for 20 years. So starting within the bracket, the simple interest rate is 10%, 0.1. We're going to multiply that by 20 years, okay? And we're going to add the 1. So I'm working within the bracket here. And then we're going to multiply that by our £100 that we started with, our original principal. So you can see at the end of 20 years, earning 10% per year on simple interest, we would have £300 at the end of 20 years, okay? Now, if we bring up the calculator and do the compounding interest, we'll start within the bracket. So it's 1 plus 10%, but it's going to be for the power of 20. So it's 1 plus 0.1 or 10%, but it's going to be now y to the x for 20 years. And we're going to multiply that by our original principal of £100. And you can see that we're getting, if we round it up, it's going to be £673. So you can see, you know, the example, compounding interest versus simple interest. If we, in the shorter periods, for 2 years, it was only different a pound, didn't seem very much. But if we were looking at compounding over 20 years, the result is dramatically different, okay? Simple interest you'd have £300 in the account at the end of 20 years, but if you're compounding it, it's 673. It's much more than double. They say that a picture is worth 1,000 words, so this is just putting into a graphic the calculations that we're doing on the previous slide, and it's the effects on savings of simple and compounded interest. So we're looking at the example of £100 invested for 20 years at 10% interest. And if we use simple interest, so that the interest every year was £10, then we know that at the end of 20 years, our balance would be the principal plus the interest that we've earned. You can see 20 years times £10, that would be £200 of interest. Our balance at the end of 20 years would be £300, okay? But if we're earning interest on interest, our balance at the end of 20 years using compounded interest would be £673, quite a bit higher. So just a quick practice question from the learning ecosystem to check our understanding. This is classified as an expert question. 2 banks each pay the same annual interest rate on their deposits. One bank pays simple interest, whereas the other bank pays the same rate compounded annually. If the same amount of principal is invested at each bank at the start of the year, at the end of the first year, the bank balances will be A, the same in both banks, B, highest in the simple interest bank, or C, highest in the compound interest bank. This question is not so difficult, but it brings up the issue of reading the questions very carefully, because I highlighted here in bold and green that it's saying that, you know, if the same amount of principal is invested at each bank at the start of the year, at the end of the first year, the bank balances will be the same, okay? A is correct. Interest earns interest in the compound interest bank, whereas it does not in the simple interest bank. But during the first year, however, there is only principal in both banks. At the end of the year, therefore, both bank balances will be the same. The principal plus the same amount of interest from both banks. In subsequent years, the balance in the compound interest bank will be higher because at the start of each year, after that first year, the account will earn interest on both the principal and the accumulated interest. So I just cut and pasted in here to the solution, the exact example that we used, and just wanted to remind you that at the end of the first year, the bank balance was exactly the same. However, in the next year, if it's simple interest, then the interest earned is always going to be the same on simple interest, £10 per year. You can see that the balance is going to be 121, but with using the compound interest, we're going to earn the 10% on the balance at the beginning of the year, so our interest was higher, and so at the end of the second year, our balance is going to be higher. So I put in bold green there, at the end of the first year. Now, if that said at the end of the second year, then the correct answer would be C. So that's really the importance of reading the questions very carefully and picking up on the key words, because in this case, it's I can change this question just by changing one word. If I change the first to second or third, then the answer is going to be different. So I wouldn't really consider that to be a trick question, but it just is highlighting the importance of reading the questions very carefully. The next thing that we're going to look at is annual percentage rate, APR, and effective annual rate, which is EAR, can be abbreviated to, okay? So unless stated otherwise, interest rates are stated as annual rates. The rate quoted is often using the annual percentage rate, which is a simple interest rate that does not involve compounding. A widely used rate is the effective annual rate. This rate involves annualizing through compounding a rate that is paid more frequently than annually, usually monthly, quarterly, or semi-annually. So the equation here is showing how we calculate the effective annual rate. Now, you don't need to do the calculations on the exam. However, it's just it's just showing the algebraic formula. So to calculate the effective annual rate, it's brackets 1 plus the annual percentage rate divided by the number of periods per year to the power of the number of periods year minus 1. Okay? So in the text and on this table, it's showing the example of the simple interest rate, or APR, annual percentage rate, and then showing the compounded interest rate, or the effective annual rate. Okay? And you can see in all cases, the compounded or effective annual rate is going to be higher than the simple interest rate, annual percentage rate that has been quoted. Okay, so that's the first thing to note. The second thing to really note is that the more frequently you compound, the higher the balance you're going to have at the end of the year. Okay, so if I was investing that £100 and I was earning 10% semi-annually versus annually, and it's compounding, then I'm going to have a higher balance at the end of the year. Okay, so the more frequently we compound, the higher our balance is going to be. So again, you don't need to do these calculations, but you can just see, how do I calculate if the simple annual interest rate is 15.24% on a credit card, but interest is compounded daily? You can see the effective annual rate is 16.46%. So again, it's the brackets 1 plus the APR in the numerator divided by 365 days, because it's daily, to the power of 365 minus 1. Again, you don't need to do the calculations, but I'll just bring up my calculator here to show you. So the in the numerator, it's 0.1524. Okay, that's the APR. We're going to divide by 365. Okay, we're going to add the 1. And then we're going to do y to the x, 365, and we minus 1, and you can see 0.16459. If we multiply that by 100 to make a nice round number, you can see that we've got 16.4589, which is rounding to this 16.46%. Okay, so the next example is a bank deposit. And the APR is 2.4% monthly, which would be 0.2% times the 12 months. So the effective annual rate would be 2.43%. Okay, so again, bringing up the calculator, if I'm in my numerator, 0.024, we're going to divide by monthly, 12. We're going to add the 1. Y to the x, it's monthly, so it's 12. Okay, minus 1 gives us 0.02427. Multiply that by 100 to get a nice round number, and you can see 2.42658. We've rounded that to 2.43%. Okay, I won't do the in the interest of saving time, I won't do the last loan on the quarterly. But I just want to show you something. This is, again, above and beyond the call of duty, because you don't need to make the calculations. But there is a functionality on the calculator, and some of you may want to progress and build up your skills. So it's not going to take long to show you. I just want to show you that there is a functionality on the Texas Instruments BA2 Plus calculator. It's called interest rate conversion, and it's a second functionality. So if I go here, so bring up the calculator, second interest rate conversion, I'm going to put in that nominal rate. That's the APR, okay? So we call that the nominal rate. And 15, we don't have to put it in percentages here in decimals. We can just put in 15.24, and I hit enter. And then I can arrow up, and it's giving me the compound periods per year, which was daily, 365. I'm going to hit enter. I'm going to arrow up, and it's giving me the effective. I'm going to hit compute, and 16.4589. So that's a lot easier than doing the algebra if you know some of the calculator functionalities. Again, not required to do the calculations for the CFA Institute Investment Foundations program, but so this is a nice to know, not a need to know. We can build our skills, okay? So if we do the bank deposit, we can do second interest rate conversion, put in that nominal rate or the APR, 2.4%, hit enter, arrow up. Now the compounding periods per year is 12, it's monthly. So we're going to hit enter, arrow up, and here we can hit compute. It's giving us 2.42658. That's rounding to the 2.43. So now, not using the algebra, I'll do the third one just very quickly. You can see how fast that is. So, second interest rate conversion, it's 6%. We're going to enter that as the APR. This is going to be quarterly, so that's 4 quarters per year. So that's 4. Enter, arrow up. I'm going to hit compute. 6.13636. Yes, that's rounding to 6.14. So that's a little bit of calculator skills for you. Nice to know, not need to know. But I find sometimes using the functionality on the calculator is a lot easier than using the algebra. Now, for the CFA Institute Investment Foundations program, again, you don't need to memorize that formula or do the calculations for the test. Nevertheless, you have to understand the difference between simple interest or annual percentage rate and effective annual rate, which is the compound interest rate. So I just wanted to show you, this is a practice question out of the learning ecosystem, and it was considered to be an expert question. So the annual percentage rate, APR, is A, simple interest rate, B, compound interest rate, or C, annualized rate when paid more frequently than annually. Okay, I hope you found that question is not too difficult. You can see the annual percentage rate, APR, the correct answer is A, it's the simple interest rate that does not involve compounding. So I just brought the table from the previous slide. You can see simple interest rate, or APR, and the compound interest rate, or EAR. So this relates to EAR, and this also relates to EAR. It's a annualized rate when paid more frequently than annually. I think you would agree that that question is not too difficult if you go through the material at a proper level. Learning outcome statement C is define present value, future value, and discount rate. Okay, so we're going to start with the present value, and you can see there's some algebraic formulas here, but don't get too worried. You don't have to do any calculations, but you need to be able to define and explain a little bit. So looking at the formula for future value first, we can see future value equals the present value times 1 plus r to the power of number of periods. And r is the interest rate. So recall, we're still carrying on with that example of having £100 and investing it at 10% for 2 years, and we would have £121 at the end of 2 years, okay? So again, the formula is future value equals present value times 1 plus r to the n, okay, number of periods. So just doing some algebraic rearrangement, you can see that present value is going to equal the future value divided by 1 plus r to the n, okay? And we can see that we have the formula for present value here. It's future value divided by 1 plus r to the number of periods. So the present value of £121 2 years from now is equal to 100, okay? Before you can calculate present or future values, you must know the appropriate interest or discount rates to use. The rate will usually depend on the overall level of interest rates in the economy, the opportunity cost, and the riskiness of the investments under consideration. So just a quick practice question to check our understanding. You can see this is from the learning ecosystem and it was classified as an expert question. The amount of money that is needed today to accumulate a stated amount in 3 years at a given interest rate is defined as the A, future value, B, present value, or C, net present value. I hope you find that that question was not too difficult. B is the correct answer. The present value is the amount of cash today that is equivalent in value to a stated amount to be received at a given time in the future when this future amount is discounted at the stated discount rate. So just carrying on with that example a little bit, just to make sure you fully understand it. Let's say that you had that £100 here, and we call that time 0, and we're looking at 3 years later, okay? So the present value of the £100, what would it be worth after 3 years if we were investing again at that 10%, okay? So if I just bring up the calculator very quickly, we start with £100, multiply it by 1.1 for year 1, and we would have £110 at the end of year 1. Bring up the calculator, multiply that by 1.1. At the end of year 2, we'd have £121, and at the end of year 3, multiply that by 1.1 again, times 1.1. You could see that we would have £133 and 10 pence, okay? 133.10. So if I just wanted to put that back into the algebra, so £100 today is the equivalent of £133 and 10 pence at the end of 3 years at a given interest rate of 10%. So if we just wanted to show you that algebraically, first of all, future value equals present value times 1 plus r to the n. Again, you don't need to do any calculations on the exam, but I just wanted to make sure that you understand this. So the interest rates is 1 plus 0.1, 10%, y to the x, 3 years, times our £100, original principal, and you can see 133.10, 133.10. And if we do the formula, present value equals future value over 1 plus r to the n, and so we're calculating the future value is £133 and 10 pence. So if we make that our future value, and again, just working our way backwards, divided by 1.1, divided by 1.1, I'm just doing it 3 times, dividing it by 1.1, and we're back to our £100, okay? So £100 in the present equals £133 and 10 pence in 3 years if we're using an interest rate of 10%, okay? So learning outcome statement D is describe how time and discount rate affect present and future values. So let's start with the future value in the example that we've been looking at. So future value equals the present value times 1 plus r, the interest rate, to the power of n. And so the first the example that we've been looking at is having £100 and investing it at a rate of 10% for 2 years, okay? So let's just bring up the calculator. So I've brought up the calculator. We're going to do 1 plus 0.1 y to the x to the power of 2 times by my £100, and we can see that the future value equaled £121, okay? So it says describe how time and the discount rate affect present and future value. And we're focusing on the future value for now. So let's say we're going to change it from 2 years to 5 years. So let's just bring up the calculator here. We're going to do same interest rate. So it's 1 plus 0.1, 10%, y to the x, 5, times by our £100, and we could see that the future value is going to, after 5 years, is going to equal 161.05. So 161 0.05 pounds. So we can see that with regards to future value, as we increase the amount of time, we're going to increase our future value. So the amount increases, okay? So that's that. So it's always going to be the opposite with regards to the present value. As we increase time, the present value is going to go down. So next thing, let's look at what happens when we affect the discount rate or interest rate. So from going from 10%, let's increase that to 12%, okay? So we're going to have the formula future value equals 100 times 1 plus the interest rate, 0.12, and we're going to start with the 2 years, okay? So let's just bring up the calculator. 1 plus 0.12, now it's 12%. Y to the x are 2 years, times our 100 pounds that we're starting with. And we can see the future value would be 125.44 equals 125.44. All right, so that is more than our 121 pounds if we invested at 10% for 2 years. If we invest for 12% for 2 years, we'd have 125 pounds, 0.44. So as we increase the discount rate or interest rate, we're going to increase the future value. And again, if we do the opposite, as we increase the discount rate, we're going to decrease the present value. And that's just a function of algebra. Present value equals future value divided by 1 plus r to the n, okay? So you can see we've got numerator and denominator. Anything you do to increase the denominator is going to decrease the present value. So if we increase the interest rate, it's going to decrease the present value. If we increase the time, it's going to decrease the present value, okay? As we decrease the r or decrease the n, we're going to increase the present value. And that's how time and discount rate affect present and future values. So we're continuing with the effects of time and discount rate on value. And we're going to work our way through the example in the text, okay? So in this example, you're assuming that you're choosing between two investments of equal risk. So you've got investment number 1 and you've got investment number 2. And because you believe them to be equal risk, you're going to use the same discount rate of 9%, okay? Both investments have the same initial outlay of 500 pounds. So for investment number 1, number 2, you're going to have an outlay of 500 pounds. So I like to draw my timeline. So for the first one, you're going to outlay 500 pounds. We call this time 0. And you're going to get 1,000 pounds in 3 years, okay? So here's year 1, there's year 2, there's year 3. At the end of 3 years, you're going to receive 1,000 pounds, okay? So the first thing that I'm going to do is I'm going to look at the present value of investment number 1. And the way we're going to calculate that, present value equals future value, which is 1,000 pounds, divided by 1 plus the interest rate, 0.09, to the power of n, the number of years, which is 3. Again, you don't have to do the math on the exam, but nevertheless, the calculation is not that difficult. And you can see the present value is 772 pounds, 0.18. Investment number 2, on the other hand, this is why, using present value, you can compare investments for different time periods and make some judgments. So here we have time 0, 1, 2, 3, 4. So we're looking at the end of 5 years. It's the same initial outlay of 500 pounds, but the choice is at the end of 5 years, you could receive 1,350 pounds, and you want to be able to compare them. So again, you would calculate the present value. The present value equals the future value, 1,350, divided by, we're using the same discount rate, 1.09, but now in this case, it's to the power of 5. So you can see that the present value of investment number 2 is 877.41. So you would want to choose investment number 2 because the present value of investment number 2 is greater than the present value of investment number 1. And that's why using present value and future value techniques allows us to compare between different investments with different timelines. Okay, so in this case, you would choose investment number 2. Now, but the example in the text is saying, wait a minute, maybe there's been a reassessment of risk, in which case you decide that investment number 2 is now looking to be more risky. So as you increase risk, you increase the discount rate or interest rate, and now you've determined that you should use a discount rate of 15%, okay? So you want to recalculate the present value. The present value equals the future value divided by 1 plus the interest rate, now 15%, to the power of 5. Remember, investment number 2, you're getting that $1,350 after 5 years. And now you can see that the present value is 671.19. So after your reassessment of risk, you can see that the present value of 2 is lower than the present value of 1. So you would actually want to choose investment number 1. Now we're moving on to learning outcome statement E, which is explain the relevance of the net present value in valuing financial instruments. Okay, so when the initial outflow for each investment is the same as in the example on the previous slide, using present values as the criterion is appropriate for comparing investments. But of course, investments may not have the same initial cash outflow, and outflows may occur at times other than at time 0. So the net present value of an investment is the present value of the future cash flows or returns minus the present value of the cost of the investment, which often but not always occurs in the initial period. Okay, so using net present value rather than present value to evaluate investments is especially important when the investments have different initial costs. Okay, so in this example, we're looking at investment number 1, but instead of initial cost of £500, we've changed the initial cost to £700. So you can see, to calculate the net present value, we're going to take the present value of the future cash flows. That's £1,000 being received after 3 years, and we're using the discount rate of 9%. But we're going to subtract the initial outlay. So again, from the previous example, the present value is £772.18. Subtract the initial outlay, now £700, not 500, and we have a net present value. So the net present value is just the present value of the future cash flows minus the initial cash outlay. That gives us a net present value of 72.18. Investment number 2, we're keeping the initial outlay at the same £500, so you can see the net present value is the present value of the future cash flows, which is £1,350 5 years from now, using this higher discount rate of 15%, which gave us a present value of the future cash flows, 671.19. Subtract the initial outlay, and we've got a net present value of £171.19. And the rule is we're always going to choose the investment that has the higher net present value. Because investment number 2 has the higher net present value, we would select it in this case. Learning outcome statement F is describe applications of time value of money. So this is example 5 from the text in the green box, and it's looking at present value and the valuation of financial instruments. So a key thing to understand is that the valuation of many financial instruments, whether it's a stock or a bond, or in this case a loan, we're looking at the present value of the future cash flows. And the present value gives us some indication to the valuation. Okay, so this loan, it's an 8% interest loan, 2 years for £100. So somebody is getting £100 today, and they're going to pay interest at 8% per year. Okay, so you can see the interest is £8 that they have to pay at the end of year 1, and at the end of year 2, they're going to pay the interest of £8 plus the principal of 100. So again, if I drew a little timeline from the point of view of the person borrowing the money, they would have £100 at time 0, okay? And then at the end of year 1, they would pay £8 in interest. And at the end of year 2, they would pay the £8 in interest, plus they're going to pay back the initial £100. Now, from the point of view from the lender, the signs are just going to be the opposite. They would have a negative £100 at the beginning of the loan. They would earn £8 interest at the end of year 1. And at the end of year 2, they would receive the £8 interest plus the £100 of initial principal that was loaned, okay? But so what we're looking at here is saying if this loan was to change hands or trade hands and an investor wanted a 10% return, what would be the value of that loan? And all we're doing is calculating the present value of the future cash flows. So you can see here, the first cash flow, we would calculate the present value. The present value equals the future value. It's the £8 divided by 1 plus the interest rate. So that's 1 plus 0.01 to the power of 1. Okay, so you can see £8 divided by 1.1 plus the present value of the second interest payment, which is £8 divided by 1.1 to the power of 2, plus the present value of the principal being repaid, which is £100 divided by 1.1, also to the power of 2 because it's at the end of 2 years. And we could see that the valuation of that loan using a 10% return or a 10% discount rate is £96.52. So we're continuing here with Learning Outcome Statement F, which is describing applications of time value of money. Okay, so many kinds of financial arrangements involve regular payments over time. For example, most consumer loans, including mortgages, involve regular periodic payments to pay off the loan. Each period, some of the payment covers the interest on the loan, and the rest of the payment pays off some of the principal, the loaned amount. Two time value of money applications that require the final balance of money to be zero are annuities, the investment products, and fixed rate mortgages. An annuity involves the initial payment of a sum, usually to an insurance company, in exchange for a fixed number of future payments of a certain amount. Each period, the insurance company makes payments to the annuity holder. These payments are equivalent to the annuity holder making withdrawals that can be viewed as negative cash flows because they reduce the annuity balance. The initial payment to the insurer is called the value of the annuity, and the final value is equal to zero. A repayment or amortizing mortgage involves a loan and a series of fixed payments. The initial amount of the loan is referred to as the principal. Although the payment amount is fixed, the portion of each payment that is interest is based on the remaining principal at the beginning of the period. As some principal is repaid each period, the amount of interest decreases over time. Therefore, the amount of principal paid increases with each successive payment until the value of the principal is reduced to zero when the loan matures, when the last payment is made. Note that adjustable rate mortgages do not fit this pattern. So the next slide, we're going to look at the example of a mortgage, and we're going to look a little bit more detail at those interest and principal payments. So in this slide, we're going to look at an example of a mortgage. So you borrow £60,000 to buy a small cottage in the country. The interest rate on the mortgage is 4.6%. Your payment at the end of each year will be £13,706 for 5 years. So the payments are being made at the end of each year. It's only an annual payment, and there's 5 payments to be made. Each payment £13,706. Okay, so you can see at the beginning of year 1, you've received the £60,000. The mortgage payment is $13,706. But how much is the interest? The interest is the $60,000, the principal, times 4.6%. So we get £2,760. That means the principal is being reduced by £10,946. How do we get that number? It's the £13,706 minus the interest that's being paid, 2,760, and that's going to reduce our principal by 10,946. So you can see here at the beginning of the year, 60,000 pounds minus 10,946 gives us 49,054 pounds. The mortgage payment is always the same. But how much is the interest? Well, the interest is based on the outstanding balance at the beginning of the year. 49,054 times 0.046 gives us 2,257 pounds. So again, total mortgage payment of 13,706 pounds minus 2,257 is going to give us a principal repayment of 11,449 pounds. So I take 49,054 pounds minus the amount of principal that's being repaid back, and at the beginning of year 3, I have a mortgage outstanding of 37,605 pounds. Again, the mortgage payment never changes. There's 5 equal payments of 13,706 pounds. So you can see in year 3, the amount of interest is 37,605 pounds, the balance of the mortgage outstanding at the beginning of the year, times that interest rate. So the interest in year 3 is 1,730 pounds. So 13,706 pounds minus 1,730 pounds is going to equal 11,976 pounds. That's how much principal is being repaid. So I don't need to finish the next 2 rows, but there's a couple of things that you can see that are happening here that are very important to notice. Number 1, you can see that in each successive year, the interest payments are decreasing in amount. Why? Because the loan is being paid back and the interest is being calculated on the mortgage outstanding at the beginning of the year. So the interest component is getting lower each year, and the principal is increasing each year. You can see the amount of principal paid back in the first year was 10,946 pounds, but the amount of interest being paid back in year 5 is 13,000 pounds. So that's the type of questions that they're going to ask you with regards to a mortgage, is that in successive years, the interest component is going down and the principal component is going up. And it's just a function of math because the total mortgage payment, the amount doesn't change, but each payment is broken into 2 components, an interest component and a principal component. And the interest component at the beginning of the loan, well, the mortgage has the highest balance at the beginning of the year, the first year, so that interest component is going to be higher than in successive years, where the mortgage outstanding balance at the beginning of the year is lower and lower. Okay, so hopefully that's not too difficult. Now, very quickly, this is definitely a nice to know, not a need to know, but you may ask yourself, where did that 13,706 total mortgage payment come from? Again, that's just, we can calculate that using some functionality on the Texas Instruments BA2 Plus calculator across this row. Now, some of you may want to advance on from the CFA Institute Investment Foundations program to do further studying where you may be using this calculator, so I just wanted to show it to you very quickly. So first of all, payments are being made at the end of the year, so we're not in any type of beginning mode. And they're annual payments, so second PY, periods per year, is set to 1, okay? So I'm going to show you how you calculate the payment. N, the number of years, is 5, so we're going to do 5N. The interest rate is 4.6%, so we're going to enter 4.6. We do that as a whole number. The present value is 60,000 pounds. That's what I'm going to borrow. That's money into my pocket, so I'm going to keep it positive. And when the loan is finished, the future value is going to be 0. And so I'm going to compute the payment, and you can see 13,705.60. So they've just rounded up to 13,706 pounds. Okay, so that's just very quickly how we can calculate a mortgage payment using some time value of money functionality on a financial calculator. I'm just following that up with a practice question from the learning ecosystem that was classified as difficult. And again, I just want to show you that you're not required to use the calculator on any of the questions in the learning ecosystem. You can see this practice question. It says, in a mortgage transaction, the amount of each fixed payment made by the borrower that represents interest, A, decreases over time, B, remains the same over time, or C, increases over time. So I think you can see that answer is not too difficult. The correct answer is A. In a mortgage transaction, the amount of each fixed payment made by the borrower that represents interest, so that's the key word. Again, this is the key point, is you have to pick up on the most important words. Interest is decreasing over time. The portion of each payment that represents interest is decreasing. The amount of principal is increasing. So again, you could see how they could change that question to get a new question. They would say that the amount of each fixed payment made by the borrower that represents principal, and that would give you increases over time, which would be C. So that's just another sort of exam tip, is that when I'm looking at practice questions in the learning ecosystem, I think how could they change it so that they have a new question but based on basically the same learning outcome statement. So in this case, the key word is interest, and interest decreases over time. But if they change that word to principal, it would change the answer. It would be, the correct answer would be C, okay? But hopefully you didn't find that too difficult. A is correct. Although the payment amount is fixed, the portion of each payment that is interest is based on the remaining principal at the beginning of the period, and that's going down because payments are being made against the mortgage. So as the principal declines, so does the amount of the fixed payment that constitutes the interest. So again, the mortgage payment is being split up. It's the same amount, but part of it is for interest and part of it is principal repayment. Okay, not too difficult. Now we're moving on to learning outcome statement G, which is explain uses of mean, median, and mode, which are measures of frequency or central tendency. Okay, so in general, descriptive statistics are numbers that summarize essential features of a data set. So a data set relates to a particular variable. For example, we could look at the returns of a particular stock or a stock market index. The data set includes several observations, that is, observed values for the variable. So we could be looking at daily returns or monthly returns or yearly returns, okay? The distribution of a variable is the values a variable can take and the number of observations associated with each of these values. Two types of descriptive statistics are those that describe the location or central tendency of a data set, for example, the average or mean. So when we're talking about the mean, it's an example of a central tendency. And we also look at descriptive statistics that describe the dispersion or spread of the data, and, for example, looking at standard deviation. So we're just going to look at the example that they have in the text. And this example, they've got 10 years, and they've got annual returns chronologically. So it's the annual return to some type of investment, okay? So in year one, there's an annual return of 1.3%, which is ending minus beginning divided by beginning is how we calculate the annual return. And if there's any types of dividends, it would be ending price minus beginning price plus the dividend divided by the beginning price, okay? So first of all, you want to understand how to calculate return. I think you should be able to know how to do that. You can see year two had a return of 2.4%, year three, 0.8%, year four, 3.7%, etc. So you can see that you have data for 10 years of returns. So if you add it all up, you get to 63%, and we can calculate the arithmetic mean, or the arithmetic average, equals 63. That's the sum of the returns divided by the number or count of returns, which is 10, and we get an arithmetic average or mean of 6.3%, okay? Now, you can look, oh, wait a minute, year 8 is a big return of 26.4. That's a bit of an outlier. What would be the arithmetic mean if we remove that value? Well, then it would be 63% minus 26.4% divided by 9, and we'd have a fairly different return for the average. It would be 4.1%. So that would be the example of, taking one data point out of a set of data if you thought that it wasn't overall representative. Now, what we've done here in the second column is that they've done an ordering. They've taken the annual returns and they've ordered them from high to low. And we need that when we start looking at the median and mode. On this slide, we've calculated the mean, which is fairly easy. It's the sum of the returns divided by the number of returns. But now we're going to look at median and mode on the next slide. And to help us do that, we've reordered the data from the lowest returns to the highest. So on now this slide, we're going to look at the mode and the median. And the mode is just the most frequent observation that we have. So you can see when we reordered the annual returns from low to high, we had two returns that were 3.7%. Because we have two returns that are the same, it's the most frequent. The mode for the annual return data would be 3.7. Moving on to the median now, if you put data in ascending order of size from the smallest to the largest, the median is the middle value. If there is an even number of items in a data set, then you average the two middle observations. So you can see here, you've got 10 observations. Because it's an even amount, we're going to take the average of the two middle observations. So you can see I did a green box here. You've got 4 observations that are lower and 4 observations that are higher than these two amounts in the middle. So you can see that therefore, because there's an even number of observations, I'm going to take the two middle amounts, I'm going to add them together and divide by 2, so I get a median return of approximately 4%. Okay, this is my own slide, and it's actually from CFA Level 1, and it's also talking about the median, but in this case, we're looking at a situation where there's an odd amount of data in terms of the count. We can see 1, 2, 3, 4, 5, 6, 7 amounts of data, okay? So they're giving us 7 stocks, and there's 2 columns, which is a consensus earnings per share and a consensus PE, price to earnings. And we learned about that ratio in the chapter with regards to financial statements, okay? So here's an application of not only looking at some accounting data, but then coming up with a median. So again, the median is the value of the middle item of a set of items that has been sorted into ascending or descending order. In an odd number sample of n items, the median occupies the n plus 1 divided by 2 position. So you can see in this case, there's 7 items, so n plus 1 equals 8 divided by 2, so it's going to be the 4th position. But you don't know that amount until you do a reordering, in this case from the lowest price earnings, 10.7, to the highest, 2.047. So when there's an odd amount of items, you can use the formula n plus 1 divided by 2. Gives you, in this case, 7 observations equals 8 divided by 2 equals 4th position. So therefore, I've highlighted it there. That, in that case, that's your median. The median is 13.94, which is also, it's an observation of one of the data points, okay? The reason why I gave you that extra example from the CFA curriculum is because in the learning ecosystem for the CFA Institute Investment Foundations program, considered to be an expert question is this following question. One of the numbers in a data set happens to be the median of the sample. Which of the following conditions could give rise to this situation? A, the median value is also the average. B, there is an odd number of items in the data set. Or C, there is an even number of items in the data set, and the two middle rank numbers are different in value. So the correct answer is B. There is an odd number of items in the data set. So if one of the numbers in the data set happens to be the median of the sample, it means that there's an odd number of items in the data set, and that's why I showed you that example with regards to the 7 items of PE data that we sorted, and then we used the formula n plus 1 divided by 2, and we determined that the 4th data set is indeed the median, because there would be there were 7 items, so there would be 1, 2, 3. There's the 4th, 5, 6, 7. There'd be 3 items to the right of it and 3 items to the left. Okay, so for the median to be one of the numbers in a data set, there must be an odd number of items in the data set, or if there is an even numbers in the data set, the 2 middle values must be the same. Okay, in the later case, summing the 2 middle values and dividing by 2 will return the same value. So a little bit of a tricky question, but hopefully that helps you understand more with regards to what a median is and where do we find it. This is my own slide. It's just a little bit of information regarding the mode, a little bit of extra information. The mode is the most frequently occurring value in a distribution. A distribution can have more than one mode or even no mode. When a distribution has one most frequently occurring value, the distribution is said to be unimodal. However, if a distribution has 2 frequently occurring values, then it has 2 modes, and we can say it's bimodal. If the distribution has 3 most frequently occurring values, then it's trimodal. When all the values in the data set are different, the distribution has no mode because no value occurs more frequently than any other value. Stock return data and other data from continuous distributions may not have a modal outcome. When such data are grouped into intervals, however, we often find an interval, possibly more than one, with the highest frequently, and that's the modal interval or intervals. So now we're moving on to exploring the geometric mean. So first of all, we're going to use the same data that we've been looking at. We had this 10 years, and we had the annual return chronologically. So first thing that we did is we calculated the arithmetic mean, which is the average, which is the sum of the numbers divided by the count of the numbers. So 63% divided by 10 years gave us an average return of 6.3%. Okay, but when we're looking at investment returns, it's important that we use the geometric mean. And again, you don't need to calculate the geometric mean for the exam, but here's the formula how to calculate it. The formula is big brackets, 1 plus the return, first return, times 1 plus the return 2, plus 1 plus return 3. Anyhow, you multiply them all together, and you put it to the power of 1 divided by the number of returns minus 1. Now, I won't work through this on the calculator, but here it is. You can see the geometric return, big brackets, 1 plus return 1 times 1 plus return 2 times 1 plus return 3. This is where I'm getting the returns from, plus 1, 4, etc., to the power of 1, to the power, 1 to the 10th minus 1. So we get an answer for the geometric mean or geometric return of being 6.1%. So the important thing to note here that the geometric average is less than the arithmetic average, and that's important because the annual returns are varying from year to year. The geometric average will be lower than the calculated arithmetic average. So when we're looking at investment returns, it's always important that we use the geometric mean. And I'm going to show you an example why. Okay, this is my own slide. It's not in the text, but it's an example of why we use geometric mean returns when we're looking at investments. Okay, so when looking at historical returns on investments, we want to use geometric averages. This quick example will show you why. So in this example, we start with 10,000 US dollars, and we have the following returns for 4 years. In first year, we had 10% return. Second year, there was negative 25% return. Third year, positive 21% return. And in year 4, there was a positive 6% return. So the arithmetic average would be 3%. Plus 10 minus 25 plus 21 plus 6 divided by 4 gives us 3%. So if we use that and we calculated, the $10,000, how much would we have at the end of 4 years? Again, using my simple way, 10,000 times 1.03 times 1.03 times 1.03 times 1.03, we'd get a total of $11,250.08. But that is not what our actual balance would be. So let's do the math again. We have $10,000 at the beginning of the first year, and we earned 10%. So at the end of the first year, we'd have $11,000. Beginning of the second year, we have $11,000, but we have a negative return of 25% in year 2. So at the end of year 2, we would have $8,250. $8,250 at the beginning of year 3 times that year 3 21% return, we would have $9,982.50 at the end of year 3. Finally, at the beginning of year 4, we have $9,982.50 times the 6% return for year 4. And you can see here I put in bold and green that at the end of 4 years, we'd have $10,581.45, and that would be our actual balance. So we cannot use the arithmetic mean to calculate when there's variability in the returns, because it's not going to give us the right answer. If the returns were 10% minus 25%, 21%, 6%, you started with $10,000, what would your balance be at the end of 4 years? If you use the average, you'd calculate $11,255.08. That's a lot more than the actual amount that you would have of $10,581.45. So again, you don't need to calculate on the exam any calculations or recall the formulas. But again, here's the formula for a geometric average, or we could rewrite it. To the power of 1n is just the n root to a square. Anyhow, so you remember it's 1 plus return 1 times 1 plus return 2, which was negative, times 1 plus return 3 times 1 plus return 4 to the power of 1 divided by 4 minus 1 times 100. If we work our way through that math, you can see that the geometric return is 1.42296, and that's a lot less than the 3% arithmetic return, okay? So using that geometric average, though, if we take that $10,000 and do it the easy way, multiply it by 1.0142296 4 times, you could see that the balance is 10,581.45, and that's the correct balance that we would have if we started with $10,000 and in the first year had a 10% return, second year negative 25% return, third year positive 21% return, fourth year positive 6% return. And that's why we use geometric averages when we're looking at investments. So that's the correct balance in the account after 4 years. Using the geometric average adjusts for the fact that after a negative year, there is less balance in the account on which to apply the following year's returns. It is important not to use arithmetic averages when looking at average annual investment rates of return, and that's why we learn a little bit of math and statistics, because it's the application in the investment industry. These are the foundations that we need. So now we're moving on to learning outcome statement H, which is explain uses of range, percentile, standard deviation, and variance, which are measures of dispersion, okay? So the first thing that we're going to look at is range, and range is fairly easy to understand. It's the highest value minus the lowest value. So again, if we're looking at that data that we've been using for the 10 years of investment returns, we're using the column where it was sorted. We could see that the range, the highest minus the lowest, 26.4 or 0.264, minus the 0.8%, which is 0.008, gives us a range of 25.6%. Now again, if the highest return, if you wanted to omit that for some reason, you thought that was some kind of an outlier, then the range would be 8% minus 0.8%, and that would be 7.2%, which is quite different, okay? So moving on now to percentiles, if there is a large number of observations ranked in order of size, the range can be divided into 100 equal-sized intervals, and the dividing points are termed percentiles, okay? So the 50th percentile is the median, and that divides the observations so that 50% are higher and 50% are lower than the median. So the very important thing to understand here is if we talk about the 20th percentile, is the value below which 20% of the observations in the series fall. So a very quick question from the learning ecosystem. Difficult categorization. On a recent examination involving several hundred candidates, Dave's score was in the 75th percentile, Mary's was in the 15th percentile, and Pablo's was in the 20th percentile. Which of the following statements is correct? A, Mary had the highest score. B, Pablo earned the median score. Or C, Dave's score was above the median. So the correct answer is C, Dave's score was above the median. The 50th percentile is the value that divides the observations with 50% higher and 50% lower, and is thus the median. Therefore, the 75th percentile is the value below which 75% of the observations in the series fall. Dave's score is thus the highest. 75% of the others are lower and is above the median. So A is incorrect because the lowest score would be in the 15th percentile, and B is incorrect because the median score is the 50th percentile, which Pablo did not achieve. So now we're moving on to some measures of dispersion, which are variance and standard deviation. And standard deviation is the square root of variance. Again, you don't need to know memorize the formulas or have to do any calculations, but here I'm giving you the steps on how to calculate variance, and we're going to see a little bit of application, okay? So step one, you're going to calculate or use the returns given for each period and sum up the returns. Step number two, you're going to calculate then the average return, which is the sum of returns divided by the number of returns. So far, so good. We've seen that already. So step number three, though, we're going to subtract the average return from each period of return. Then step number four, we're going to square that result. Step number five, we're going to add the sum of the squares. Step number six, we're going to divide by the total number of periods minus 1 if it's a sample, and this gives us the variance, okay? And step number 7, we take the square root of the variance, and you've got the standard deviation. So here we have it from the textbook, the nomenclature. We can see that standard deviation is equal the square root of the sum of the returns minus the average returns squared, okay? So divided by n, it's not a sample, they're using a population. If it was a sample, it would be n minus 1, okay? But let's not worry about that. So here you can see it's just another nomenclature, and this is one of the difficulties if you don't have a strong background in math, is that sometimes you can see different formats. So here for a population, you can see that the variance is the sum of the return minus the average returns squared divided by n, and the standard deviation is simply the square root of the variance, okay? So this is my own slide. It's the steps on how to calculate the variance, and standard deviation is the square root of the variance, okay? Not too difficult. When you see an example, it gets a little bit easier. Okay, we're going to work through the example that they have in the textbook just to help your understanding. And what we're looking at here is to illustrate the calculation of standard deviation for an example of a 3-year investment that returns 8% or 0.08% in the 0.08 in the first year, 3% in the second year, 7% in the third year. So the first thing that we're going to do is we're going to calculate the arithmetic mean, and that's 6%, which is the sum of the returns divided by the number of returns. So 8 plus 3 is 11, plus 7 equals 18. I don't even need my calculator. 18% divided by 3 gives us our 6%. So that's the first step. Is we didn't need to calculate the returns. They were given to us. So the next step was to calculate the average return. So we've got our average return of 6%. Then we know that the next step is to take our return. So we see our first return was 8% minus the average return, and then we're going to square it. Plus return number 2 minus average return squared, plus return number 3 minus average return squared, and we're going to divide by 3, okay? Standard deviation is the square root of the variance. So what we're calculating here under the square root sign is the variance. So I'm not going to bring up the calculator to go through all the steps, but you can see you can work your way through the math, and you can see that the standard deviation is 2.16%, okay? So there's the example from the textbook giving us the formula. X is the observation. You can see that's our return 1, return 2, return 3. So it's return minus average return, square it, add them all up together, divide by the number of returns, okay? So the differences between the observed values of the returns and the mean value capture the variability of the returns. So again, these differences are summed and squared. Note that because the differences are squared, what matters is the size of the difference, not the sign of the difference, okay? So the sum is then divided by the number of observations, and finally the square root is given. The value before the square root is known as the variance, which is another measure of dispersion. The standard deviation is the square root of the variance. The standard deviation and the variance capture the same thing, how far away from the mean the observations are. The advantage of the standard deviation is that it's expressed in the same unit as the mean. So you can see here the standard deviation is 2.16%, okay? The variance is just a number, so it doesn't give us as much insight. So larger values of standard deviation relative to the mean indicate greater variation in a data set. Also, by using standard deviation, you can determine how likely it is that any given observations will occur based on its distance from the mean. Okay? I'm not going to spend a lot of time on this slide. What it's showing is that the previous slide, we're just showing how we calculated the standard deviation for that example that had 3 returns. But again, this slide is just showing we're going back to that data where we had 10 returns, and we're calculating the standard deviation of the returns. And you can see that the standard deviation in this case was 7.1%. Again, you're not required to memorize the formula or have to do the calculations, but this gives you all the data that you need to fully comprehend it. So now we're moving on to learning outcome statement I, which is describe and interpret the characteristics of a normal distribution, okay? So here we've got a graph of a normal distribution, and it looks like a bell curve. The shape of the curve is symmetrical with a single central peak at the mean of the data. And because it's a perfectly symmetrical distribution, because it's a normal distribution that we're looking at, the mean, the median, and the mode are all going to be identical here, okay? So in this example, the mean equals 0, all right? So because the shape of the curve is symmetrical, it means that 50% of the distribution falls to the left of the mean and 50% of the distribution falls to the right. The shape of a normal distribution depends on the mean and the standard deviation. The mean of the distribution determines the location of the center of the graph, and the standard deviation determines the height and width of the curve. When the standard deviation is large, the curve is short and wide. When the standard deviation is small, the curve is tall and narrow. The total area under the curve, as we mentioned, or the bell, is 100% of the distribution. So the area under the curve that is within 1 standard deviation of the mean is about 68% of all observations. We can see that here, 1 standard deviation to the left plus 1 standard deviation to the right, we're capturing 68% of all the observations. That means 32%, approximately 32%, are to the right and to the left of a greater and less than 1 standard deviation. So you can see you'd have about 16% on either side. Okay. The area under the curve within 2 standard deviations, the mean, adds up to about 95%, okay? So given a mean of 0 and a standard deviation of 1, about 95% of the observations fall between -2 and +2, and 5% of the observations are more than 2 standard deviations from the mean. A quick practice question from the learning ecosystem. The proportion of observations that fall within 1 standard deviation above and below the mean of a normal distribution is approximately A, 50%, B, 68%, or C, 95%. You can see the correct answer is B, all right? B is correct. 68% of the observations fall within 1 standard deviation of the mean of a normal distribution. So we're looking under the bell curve, this area here, 1 standard deviation to the left, 1 standard deviation to the right, we're capturing about 68%. 95% fall within 2 standard deviations. So you can see that, I could easily change this question again by changing one word, change this 1 to 2, and the correct answer would be C. So that's what I'm doing when I'm looking at these practice questions. I'm saying, okay, first of all, do I understand it? Do I know where the data came from? And then number 2, I'm kind of anticipating how could they change this question to make a new question, and do I fully understand it? So again, some of the things that I would point out is that if approximately 68% of the observations are within one standard deviation, it would mean that 32% are outside of that, which would mean approximately 16% to the right and 16% to the left, okay? Or if we're looking at outside of 95%, it would be 5% are falling outside. So to the right-hand side would be 2.5% approximately, and to the left would be 2.5% approximately. But definitely the two numbers that are very most important with regards to a normal curve is that 68% of the observations are following plus or minus 1 standard deviation, and 95% of the observations are falling in plus or minus 2 standard deviations, okay? Not too difficult. It's saying it's a difficult question. Again, not too difficult if you got to do a little bit of memorizing and then anticipate how that question could be changed. So now we're going to look at fat and thin tails, which is in the text. And the observations that are more than a specified number of standard deviations from the mean may be described as lying in the tails of the distribution. So when you're looking out here, further to the right and left, we're talking about the tails of the distribution, okay? So assuming that returns on a portfolio of stocks are normally distributed, the chance of return being in the left tail, more than 2 standard deviations from the mean, would be an example of an extreme loss, and it's less than 2.5%. That's what we said. Here's 1 standard deviation minus, 1 standard deviation plus, negative 2 standard deviations, plus 2 standard deviations. So we said 95% of the observations are within 2 standard deviations, means 5% outside of that. So if we were moving to the left, we'd know that 2.5% of the observations would be to the left of negative 2 standard deviations. So that would be a extreme loss, okay? Out of 200 days, 5 days are expected to have observations that are more than 2 standard deviations from the mean. During the financial crisis of 2008, the losses that were incurred by some banks were approximately 25 standard deviations from the mean. So to put this in perspective, if the returns are normally distributed, a return that is only 7.26 standard deviations below the mean would be expected to occur once every 13.7 billion years, okay? So that's the approximate age of the universe. So thus, the frequency of extreme events during the financial crisis of 2008 was much higher than predicted by the normal distribution. So this inconsistency with a normal distribution is often referred to as the distribution having fat tails, meaning the probability of observing extreme outcomes is higher than that predicted by a normal distribution that has thin tails. The exhibit shown in the slide gives examples of bell-shaped distributions with much fatter and thinner tails than the normal distribution. The curve with the solid line represents the normal distribution. The curve with the dashed line, which is you can see which is blue colored, is with fatter tails than the normal distribution, and the curve with the green dotted line is an example of a distribution that has thinner tails than a normal distribution. So now we're moving on to the final learning outcome statement J, which is describe and interpret correlation. We just got a couple of slides on this. So another way of using and understanding data is identifying connections between data sets. So the strength of a relationship between two variables, such as growth in gross domestic product and stock market returns, can be measured by using correlation. Essentially, two variables are correlated when a change in one variable helps predict change in another variable. If both variables change in the same direction, then the variables are positively correlated. So again, I say a picture is worth 1,000 words. This is not in the text, but I've got it from a website. Math is Fun. I just put the address there. And you can see here, this is a perfect positive correlation. It's upward sloping because an increase in one variable is leading to an increase in the other variable. On the other hand, perfect negative correlation, the graph is downward sloping because an increase in one variable is leading to a decrease in the other variable. Okay, so essentially two variables are correlated when a change in one variable helps predict the change in another variable. If both variables change in the same direction, variables are positively correlated. So for example, for traders at an investment bank, salary and age are positively correlated. If salaries increase as age increases. If the variables change in the opposite direction, then they are negatively correlated. For example, the size of a transaction and the fees expressed as a percentage of the transaction are negatively correlated. If the larger the transaction, the relatively smaller the associated fees. When there is no clear tendency for one variable to move in a particular direction, up or down, relative to changes in the other variable, then the variables are close to being uncorrelated. So we can see that here in the middle, where there's a change in one, and it's you can't really see any observable pattern to the change in the other. Okay. It is difficult to find two variables that have absolutely no relationship, even by chance. So an important thing to understand is that correlation is measured by the correlation coefficient, which has a scale of -1 to +1. So you can see it falls within a range, the correlation coefficient. Perfectly negative correlation is -1, and perfectly positive correlated is +1. If it's above 0, then you're looking at some positive correlation that's increasing. If it's below 0 and it's negative, then we're looking at low negative correlation to perfect negative correlation. So it's important to understand that it goes from -1 to +1, and 0 would be absolutely no correlation. Okay. So it's important to understand that the number gives us some indication with regards to the strength. So 0.9 is more highly positively correlated than 0.5, okay? For example, there may be a high correlation between stock market index returns and expected economic growth, okay? So if economic growth in the future is expected to be high, then the returns on the stock market are also expected to be high. We would have a very a high positive correlation, okay? So this slide is looking at correlation versus causation, and it's important to realize that correlation does not imply causation. So for example, you may notice that historically in the United States, stock market returns and snowfall are both higher in January, and from that you may assume a correlation. But there's no causal relationship between them. Snowfall does not cause an increase in stock market returns, and an increase in stock market returns does not cause snowfall. So that would be a spurious comparison. There may be situations in which a correlation implies some causal relationship, but the causality does not go both ways. So for example, a high correlation has been found between power production and job growth. It may follow that the more workers there are, the more power is being consumed, but it does not necessarily follow that an increase in power generation will create jobs. Okay, this slide is looking at correlation and its role in diversification. So correlation is important in investing because the rise or fall in value of a variable may help predict the rise or fall in the value of another variable. When two or more securities that are not perfectly correlated are combined in a portfolio, there is normally a reduction in risk, measured by the portfolio's standard deviation of returns. So as long as the returns on the securities do not have a correlation of +1, that is, they are less than perfectly correlated, then the risk of the portfolio will be less than the weighted average of the risks, and the securities in the portfolio because it is not likely that all the securities will perform poorly at the same time, okay? And there's a lot of math behind that, but we don't get into that in the investment foundations program, okay? How to calculate, if we look at the return for a portfolio, the returns for a portfolio are simply the weighted average. But if we look at the standard deviation of a portfolio, it's not the weighted average of the individual standard deviations. We have to look at the correlation, okay? And anyhow, it's just a little bit of math that we look at higher levels. So the practice of combining securities in a portfolio to reduce risk is known as diversification. An extreme example of an undiversified portfolio is holding only one type of security, or we call that having all your eggs in one basket. This approach is risky because it is not unusual for a single security to go down in value by a large amount in 1 year. It is much less common for a diversified portfolio of 20 different securities to go down by a large amount, even if they are selected at random. So if the securities are selected from a variety of different sectors, industries, company sizes, asset classes, like stocks and bonds and markets, it's even less likely. One caveat is that the benefit of diversifications are much reduced in periods of financial crisis, okay? So in such periods, the correlation between returns on different securities and different asset classes tends to increase towards +1. Okay, this is an extra slide, and it's just meant to complement the text a little bit. It's my own slide. And the source is from the JP Morgan Guide to the Markets. You can see the date is as at September the 30th, 2018. This is a publicly available document. If you just Google search JP Morgan's Guide to the Markets, you'll be able to find this. But it's a nice little graphic because it's showing us correlations and volatilities with regards to different asset classes. So the asset classes is US large cap stocks, Europe, Asia, Far East stocks, emerging market stocks, bonds, corporate high yield bonds, municipal bonds, currencies, emerging market debt, commodities, real estate investment trusts, hedge funds, and private equity. And so here within this box, it's showing the correlations. And on the right hand side, we're looking at the annual volatilities. So for example, if we're looking at the S&P, the U.S. large cap, and that's being made up of, if we look down here, what is the U.S. large cap? It's the S&P 500 index, that the annual volatility is 15%, okay? And you can see this data is from, it's 10-year data. It's based on a quarterly return from 2008 to 2018, okay? So it's 10-year quarterly returns. And you can see, as you would expect, emerging market equities have a higher risk, maybe higher return, okay? And so within here, you can see that the correlation between bonds and U.S. large cap stocks, and indeed these other categories of stocks, Europe, Asia, Far East, and emerging market equities, is negative. They're negatively correlated, and that starts to show you the benefits of diversification. So number one, bonds, you can see, have a lot less volatility. That's a key point to understand than stocks. They're going to have a smaller return, and they are negatively correlated. So if we're making a portfolio that's going to reduce our volatility, we're going to combine some stocks and bonds, okay? It's as simple as that. So again, just one last slide. This is from the Guide to the Markets, U.S. data as of September 30th, 2018, the JP Morgan Guide to the Markets. And so this is quite neat. It's looking at from 1950 to 2017. So on this axis, you've got returns on the y-axis, and on the x-axis, you've got time. You can see it's rolling 1 year return, then 5 year rolling return, 10 year rolling return, and the 20 year rolling return. So the green bars is looking at stocks, and that's the S&P 500, okay? And what that's showing is that if you're only looking at 1 year, calendar year, the maximum return on the S&P 500 has been 47% during that time period, and the negative return was 39%. That was 2008. In fact, peak to trough was more like 54%, but we're looking at annual total returns, calendar year returns. So you can see the variance, and therefore the standard deviation, or the dispersion of returns for stocks, is quite big. You can have the best year was 47% return, and the worst year was 39% return. Okay, so you can see the average total return was 11.2%, but that's with a lot more variability. If we look at bonds, you can see that the best return was plus 43%, but the negative return was only negative 8%. So stocks represent the S&P 500 Shiller Composite, and bonds represent a they're using some type of index. So you can see that the second key point to pick up is that the average total return is less on bonds, but so is the variability. Okay, so is the dispersion of returns. So therefore, if I create a 50-50 portfolio, you can see that I've got less variability, less volatility than having a 100% stock portfolio. So again, number one, because there's less variability in the returns to bonds, and then number two, because we saw in the previous slide that there's a negative correlation between stocks and bonds. Okay, so that's the very important thing to see. So if we looked at the growth of 100,000 over 100 years, stocks have got the higher return, 11.2%. So if you had all your eggs in the stock basket, after 20 years, you'd have $840,000. If you had 100% in bonds, you'd have $316,000. And if you had a 50-50 portfolio, after 20 years, the growth of $100,000 would be at $556,000. Okay. So the next important thing to understand is that the longer we go through time, there is less variability, less dispersion on the rolling averages on the stocks. So in fact, if you look at a 10-year rolling average, you can see that your maximum loss was only negative 1%, and that's from 2008. In fact, in the past, if you took any period of time and went 10 years later, if you looked at the total return on the S&P 500, you've never would have had a loss. Okay. And indeed, if you go to the 20-year rolling return, you can see that there's no chance of having a loss. So time is your friend. Okay. So that was I wanted to just finish off. We're studying some quantitative concepts, but you have to understand, why are we studying it? It's because it's the application to the investment industry, in particular in terms of building portfolios. So, being able to calculate or understand variance and standard deviations, the dispersion of returns is important. And then because that gives us some insight to risk. Risk is measured by standard deviation. The higher standard deviation, the higher the risk. And the next thing that we're looking at is correlations. And correlations is important because it's when we start combining different assets from different asset classes, when they have correlations of less than 1 or indeed negative, that is going to reduce the standard deviation of the portfolio. It's going to reduce the risk of the portfolio. Okay, so that's the last slide for this topic in this chapter. And that's the conclusion for this video, which was Module 3, Input Tools, for Chapter 8, Quantitative Concepts, for the CFA Institute Foundations program. Thank you.